Hi everyone, my name is Marcin, and this video is going to be about a final project that I made together with my partner, Ibrahim Khan, for a course this past semester, specifically Applied Math 120, which is Applied Linear Algebra. Our project essentially consists of an implementation of speaker recognition in MATLAB, and you can think of it as a password checker where the computer is able to tell not only if the correct password has been inputted, but also if it's you inputting your password rather than some impersonator trying to input your password. The motivation behind showing you guys this program that we made is that it uses the fast Fourier transform, which is a very powerful algorithm that enables you to get a Fourier transform from a discrete signal, and we touched upon it briefly in class, so maybe this video will show you how, give you a more concrete example of how it can be applied to a very cool practical use. Alright, so to begin, I thought I'd just start out with a demonstration of the program itself. So the program's name is KK. That's just the first letter of each of our last names, Khan and Kostecki. So first we just like to register a password before we try to log in. I'm going to enter my name, which is just Marcin. Now the only catch is that your password has to be in the form of a single musical note, and I'll explain the reason for this later. As you see, since I'm a male, I'll choose, I'll choose a frequency of, say, 250. So now what's going to happen, I'll cycle through the instructions here. I'm going to be asked to record my password 5 times. Each recording is going to last 5 seconds. Before the recording starts, I'm going to have the note of my desired frequency played to me so that I can match it better. And so when that's going to be playing, I'm just going to hum along so I can get the hang of it. And then once the note is played, it stops, and then the program tells you to start humming. You're quiet for a split second, then you hum the note that was just played to you, and then you're silent. And then you have to be sure to hum loudly, clearly, and consistently from recording to recording. Alright, so let's get started. Great, so my first recording went well, and I'm just going to proceed through the rest of the 5. That takes kind of a long time, but so bear with me. Alright, great. So that completes registration. And now we're going to try to log in and see if our program works. Alright, so to log in, I just type in the program's name once again. And now instead of choosing 1, I choose 2 in order to log in. So the program asks me for my name, which is Marcin again. And I pick the frequency that I registered earlier, which was 250. So now I'm just going to be asked to input my password or my pass frequency once, and the instructions are just the same as for registration, so I'll just cycle through them quickly. Okay, here we go. and access granted, so recognize me. Now let's see what happens if I pick a slightly different frequency. So that's kind of akin to typing in the wrong password. Once again, I'm trying to log in. Now, instead of selecting 250, which was the frequency with which I registered, I'll select 260, so 10 Hertz higher. Noticeably different. Instructions again, and now we're going to start. Alright, access denied. So the computer recognized that I selected a different password. Alright, now to see what happens if somebody tries to impersonate me, I'm gonna get my roommate over here so he can help me out and see if the computer recognized that he's actually not me. Alright, so now I have my roommate over here who's going to try to impersonate me, and we'll see if the program is able to distinguish between him and me. So we call the program again, we choose 2 to log in, and he's going to be impersonating me, so he types in his name as Marcin, and say that he knew what frequency I had chosen for my password, so he selects 250 as well. And now he's going to go through the same process as I did to log in. Okay, ready?
Mm-hmm.
Alright, try to give it a shot again. Just make sure to be really quiet afterwards, and maybe start a little bit sooner.
Sure.
Alright.
Sweet.
Alright, so now that we've seen the program distinguish between 2 different frequencies hummed by the same user, as well as the same frequency hummed by 2 different users, I'd like to give a brief, kind of high-level explanation of how the program works behind the scenes. So I think that a good way to do this is to look at visual representations of the data that is given to the program and how this data is manipulated as the program executes. So first, during registration, the user provides the program with 5 recordings of them humming the same frequency. Here we have a visual representation of these 5 recordings, with each color representing a different recording. You have amplitude on the y-axis and time on the x-axis, and notice that these recordings are actually done at 200 Hertz, so a slightly lower frequency than in our example where we did 250 Hertz. So then, once the computer receives these 5 recordings, it applies the fast Fourier transform to each recording. And the fast Fourier transform is analogous to the continuous Fourier transform, except that it's able to identify the coefficients, it's able to decompose discrete signals into its component frequencies. And by discrete signal, I mean a signal where the sound is sampled not continuously but at discrete points of time, which of course is a necessity in real life. Once the fast Fourier transform gives us these coefficients, we take each of the coefficients and we square them, because some of them might be imaginary. So by squaring them we get a real number, and this gives us essentially a proxy for the amplitude of the coefficient on each frequency. And if we compare the amplitudes of the coefficients across all the different frequencies and plot it with here the amplitude on the y-axis and the frequency on the x-axis, we can see what are the most important or the salient frequencies in our recordings. So again, each of the colors represents a different recording, and you can see that they agree with each other. That the most important frequency is 200 Hertz, which we see over here, And then you also have some other frequencies which are essentially over and undertones of 200 hertz. So you have 400 hertz here, you have I guess like 100 hertz here, 50 hertz, and so on. Alright, so once we've applied the fast Fourier transform to our recordings and found the coefficients of the component frequencies and squared these coefficients to obtain their magnitude, we then apply a function in MATLAB called find peaks, which we specify certain parameters so that the function returns to us the frequencies that correspond to the 20 largest coefficient amplitudes in the recording. And what we obtain is essentially a matrix with 5 columns, each column containing these 20, you could call them most important frequencies for that recording. And once we have this kind of matrix, we look at each frequency and see how many times, or rather in how many other recordings it's also appeared. We then take only those frequencies that appeared in at least 4 of the 5 recordings and consolidate those to form what we call a key. So here we have the key that was formed for me when I was doing my recording at 250 hertz. So we see that 250 is present, we see that 125, half of 250, is also present, and then we notice that there's a whole host of other frequencies, the nature of which will become apparent in a second. Alright, so now that we have our key, we can actually try to log in, and as you saw me demonstrate during the login process, the user just provides a name. It could be an imposter or the genuine user themselves, and then they pick a frequency and they provide a recording of a hum at that frequency. And what this looks like is essentially the same as any of the 5 registration recordings. And then the process that this data is subjected to is also the same, almost the same as the process for the 5 registration recordings. Namely, MATLAB applies the fast Fourier transform to the signal, which gives us the coefficients of the component frequencies. We then square these coefficients to get a proxy for the magnitude or importance of each frequency in the signal. And then the difference comes in at this point where instead of keeping the 20 frequencies with the greatest coefficients squared, with the greatest amplitudes or importance, we instead keep a number of frequencies equal to the length of the key in question. So if the key in question was this one that I just showed you, which has 10 entries, we would only keep the 10 most prominent frequencies. And then once we have our key and then the 10 most prominent frequencies in our login attempt, we see how many frequencies are present in both the key and the login attempt. And if the login attempt has at least 75% of the number of frequencies that are in the key, then the user is granted access. So in this case, you would have to have 75% of 10, so at least 8. You'd have to match at least 8 of these frequencies to get access granted, and otherwise you're denied, like my roommate was. And yeah, that's essentially the crux of the program. Alright, so before I wrap up here, I'd like to discuss for a moment why this method actually works. For a case where the same user is humming 2 different notes, it's kind of intuitive to see that the dominant frequencies in each of those 2 recordings are going to be different. They're different notes. But in the case where 2 different users hum the same note, it's a little bit more subtle to realize why we'd be able to distinguish between these 2 users. So a good analogy to think about is that of musical instruments. So for instance, you can have a flute and a trombone both play the same note, but they clearly sound very different. And the reason for that is, besides the frequency of the note, the 2 instruments are also playing many other different frequencies, which we kind of saw in this graph right here. So although I was humming 200 hertz, I'm also humming some other frequencies. And if we zoom in a little bit closer, we see that in fact there's a lot of different frequencies that I'm humming. And these little frequencies that don't coincide with 200 hertz, which is right here, and its overtones like 400, 600, 800, 1000, and undertones. The frequencies that do not coincide with these like, frequencies of the note are in fact a characteristic of that's particular to my voice. So in the trombone and flute example, these frequencies that do not correspond to 200 hertz, 400 hertz, and so on are the reason you can distinguish between a trombone and a flute, and the reason you can distinguish between two users. And this is more clearly seen if we actually compare two different users. So here we have a frequency spectrum of two individuals humming 250 hertz, and green is one individual. Green represents the recording of one individual, blue represents the recording of another individual. And you see that while they match up at 150 hertz, 300 hertz, and so on, there's certain peaks that are exhibited in the green person's frequency spectrum that don't appear in the blue person. So for instance here, you have a peak for green but not for blue. And then likewise you have here a peak for blue and not for green. And then we can see this phenomena at other locations, like here, out here, and over here closer to 0. And that's the reason, if we take the 20 most important frequencies in the recording, then we're hoping that we include some of these smaller guys that will help us then distinguish between two different users. So as a final remark, I'd just like to mention that this program is far from perfect. It's really finicky, and there's lots of little things that can go wrong along the way. In this video, you saw me using it, and since I co-created it, I'm able to take care of a lot of details that might otherwise screw the process up. I don't have time to talk about all of them, but I'll talk about a few of the most important ones. The main one is the user's ability to, or rather inability to reproduce a note. And by reproduce I mean hum it the same way consistently from recording to recording. So this can be as subtle as the position of your tongue in your mouth when you hum. So for instance, I like to clench my teeth and put the tongue on the roof of my mouth, and that helps me standardize my recordings. And if you don't do that, chances are that during registration you'll hum in slightly different ways, and there's a high chance that little peaks like this one here and this one here, that help to distinguish your voice from another user's voice when you're humming at the same frequency, they don't appear in 4 of the 5 recordings, and hence they're not included in the key. And the key includes just a very small number of frequencies that are basically frequencies that correspond to the note that you chose. So for instance here it would be 250 hertz, 500 hertz, and so on. And of course an imposter can very easily replicate those. And in fact, that's exactly what happened when I was making this video. When my roommate tried to impersonate me the first time, he was successful. And I looked at my key, and there was actually only 4 frequencies in there. So I redid the registration process. I was very careful to standardize the way I hum. And then I got a key with 10 frequencies, and after that my roommate wasn't able to impersonate me successfully anymore. This is the reason why we chose a note rather than word as the password. So if you see that humming a note is difficult to standardize, so you can imagine how difficult it would be to say a word in exactly the same way, recording to recording to recording. And that's initially what our plan was in creating this project, and we quickly realized that there's no way that this is going to work. You can see in this graph the frequency spectrum of 5 recordings of the word password, and even though they kind of match up, they're nowhere near as consistent as the recordings of a note, which you saw aligned almost perfectly, except for very small frequencies. So if I can go back, so we have almost perfect alignment here, and differences, and very, very small differences. Another issue that we have is that there are a lot of parameters in the program whose values were kind of set arbitrarily or by guess and check. And for instance, we decided that a user login attempt has to match at least 3/4 of the key to gain access, and otherwise the access is denied. So the 3/4 just kind of came from us playing around with the program and seeing which values work best. And there's lots of other these parameters. For instance, how many peaks do we keep? So how many salient frequencies do we keep? We keep 20 at the moment, but we could keep 30. We could keep 10. We have 5 recordings at registration. Ideally, we'd like to have maybe 10 or 20, but there's not enough time for that. We just chose 5 arbitrarily. And then there's lots of other parameters that pertain to details of the program that I didn't go into here. So ideally, in the future, we'd like to run some kind of statistical tests on our program and mathematically determine the values that the parameters should take, rather than just arbitrarily assigning them. So those are the kind of 2 big issues with the program that pertain to what I've presented here. Well, thank you very much for listening. I'm sorry it's taken a little bit longer than I expected, but hopefully you enjoyed it, and I hope you have a great summer. Thank you very much.